our friends at IBM are continually trying to form an international combination of companies to, in fact, push technology development forward. There are still companies like Intel that are very, I would call them independent or standalone in that respect, but the cost of process development, the cost of investment has gotten to the point where partnerships are becoming more common. I mean, we've seen this in Japan, where we went from 10 standalone major semiconductor companies. We're now down to a couple, and they continue to consolidate because of the critical mass necessary to move forward. We've seen this in Europe with, in fact, the European equivalent of the focus centers to try to have a European central research laboratory which services not only European companies but also companies from around the world. So there are lots of changes here. What is constant is the problems are not simple. They are getting more expensive to address. And the investment continues to go up for leadership. So if you want to lead, you continue to have to increase the ante. And if you combine that with Gordon's observation that let's stay on an 18-month or 2-year track, and it just means that it's more exciting every year. When we started this industry, and you could look at a wafer and you could see the transistors with your naked eye, to where we are today, where you put a powerful optical microscope on these things and you see nothing, and you need a scanning microscope or a transmission scanning microscope or something else to see what you're making. It's unbelievable. Educated as a material scientist, I still look at these circuits. 2 billion transistors in one of these big complicated microprocessors. You look at cross-sections of the transistors, you see that they're not totally uniform, they're little ragged edges here and there. And you say, what's the probability that 2 billion of these things will all work kind of as they were designed, as manufactured, and the gate, it's 5 molecules thick of, it used to be SiO2 and now it's some hafnium-based stuff. But what is the probability that these things are going to work? And you say, you're crazy. Nobody can make these things. It's not going to work. But they do work. And that's what makes it so exciting. And not only do they work, but you can crank out millions of these devices. And we get better at it every year, even though it's 10 times harder, 10 times more complex than it was a few years ago. But the technology we're able to throw at it, the steady influx of bright, educated people helps. And it also helps to have these young people who you kind of look at and say, we've made Moore's Law work for 40 years. It's now your responsibility. If it fails under your leadership, boy, are you in trouble. And they say, no problem. We can make this work. But that's the excitement of this industry. I mean, who else in the world does this sort of stuff? I mean, maybe the folks who are splicing genes and doing DNA, but let's be serious for a minute. We're pumping out billions and billions and billions and trillions of transistors and circuits every day. And every 2 years we turn the knob and we take another step forward in technology capable. There's no industry anywhere that matches that. No industry anywhere. These are the most complex things that man has ever made. And you've got to be excited to be part of that. I mean, you can't even sit at the periphery and not get excited about what happens. And I walked through our manufacturing facilities 35 years ago, and I walk through them today, and it's like a history book. Fast forward from where we were 35 years ago, spinning wafers with toothbrushes to knock off silicon asperities and smoothing the surface and Q-tips rubbing this stuff, to today. I mean, you take a 12-inch diameter wafer, and you can put atomic layers down, plus or minus, kind of one molecule across the entire surface of that thing. No, it's impossible. It's absolutely impossible. Though we do it every day.